Thank you for inviting me here. It's my pleasure to be here and speaking after a quantum information theory giant like Andreas. I gave Christian a few options of possible topics, and he suggested I speak this particular one. So I'll mostly tell you about these two papers I have on my slide, which are about entanglement distillation using the measurement-based model of quantum computing and its application to quantum repeaters. But I will tell you a little bit about the role of quantum in classical communications, as well as a little bit about the actual design and build of quantum repeaters using atomic qubits, which was what actually motivated this work on measurement-based model of quantum entanglement distillation. So before I begin, acknowledge my former PhD student, Ashlesha Patel. She's now a scientist in PsiQuantum, and former postdoc, Yu Shi, who did most of the work on these two papers. Okay, so let's start with a little bit about the role of quantum processing and quantum in classical communications. So what you're seeing on the screen right now is 5 modes. So you can think of 5 pulses of light, and each one is excited in either of 2 coherent states, alpha or minus alpha. So the binary phase shifting modulation. Okay, so of 32 possible binary sequences, I've only given you these 8, which are part of your code book, and I ask you, what is the minimum probability of error of telling them apart? You can calculate that minimum probability of error by evaluating the relative inner products between these 8 code words, treat them as quantum states, and feed them into what are known as the UN, Kennedy, and Lax conditions, and evaluate the minimum probability of error, and you will get something like this pink line here, the probability of error plotted as a function of the mean energy per pulse. Now, if you had to design a receiver to tell them apart, what would you do normally in a lab? Well, you would detect each of those optical pulses one at a time. Say, for example, in this case, you probably use a homodyne detection receiver, and then you do some classical post-processing, including some soft information processing and so on. Now, it turns out that no matter what receiver choice that you use, as long as your receiver is measuring every single one of those 5 optical pulses one at a time, interspersed with some classical post-processing, there is no way you can get better performance than this blue dotted line. So in order for you to bridge between that and the Hellstrom limit or the minimum error probability, your receiver must make joint measurements, so joint detection measurements that collectively act on the entire quantum state, which cannot even be broken up into measuring each of those 5 symbols. Now, how you implement it in real life is typically using some sort of either an all optical joint measurement, or you can take each of those pulses and you can load them into qubits. This is Kaushik and Narayan Rangaswamy who led this work we did with Henry Pfister on borrowing ideas from classical belief propagation decoding. And once you have loaded the relevant information into qubits, it turns into a quantum circuit. Recent paper I'll just point out, we'll not talk about it. Mark Wilde and I did a paper on quantum polar codes back in 2011, 2012, that showed that how you can design an error correcting code and a receiver design that can achieve the Holevo capacity limit. So in this paper, we come up with a strategy that after you load these coherent state pulses into atomic memories using a variant of what is known as the Duan-Kimball protocol, that you can design a receiver which looks like a basic quantum processor on those atomic qubits that can achieve the same performance that we had proposed in that quantum belief propagation decoder, the successive cancellation decoder for the quantum polar code. Very simple example of a joint detection receiver, a paper I wrote in 2011 called the Green Machine. The idea is very simple. So you have these binary Hadamard code words, so binary phase shifting modulation. So these pluses and minuses are coherent state symbols. And depending upon which pattern of coherent states you put in through this linear optical circuit made up of beam splitters, you get all of the photon energy in one of these outputs. And then if you do the math of the calculate the capacity, what you will see is that your bits per photon you can achieve. This black line is the best performance you could get with BPSK with any single symbol receiver. Caps off at 2.9 bits per photon. With this particular receiver, you can exceed that. And this was an experimental demonstration we did 15 years from that theory paper that did the first demonstration of super additivity in classical communications. So there's a lot of very interesting theory work and experimental work in this area that can bring both use of quantum processing in atomic quantum processors, as well as novel uses of, say, squeeze light and linear processing in the optical domain before you detect the code words to get towards the quantum limit of communications capacity. Okay, so with that, let me talk about quantum communication, sending qubits over a quantum channel. And then I'll talk about entanglement distillation and quantum repeaters. Okay, so sending qubits over a noisy quantum channel is a task that is very closely connected to generating heralded entanglement over a noisy quantum channel. Why? Because if I have entanglement, I can use that to send a qubit using teleportation. And vice versa, if I can send a qubit reliably over a noisy channel, then I can locally create entanglement and send a qubit over to the noisy channel, and I can establish entanglement. So these two tasks are related to each other very closely if I allow for two-way classical communications as a free resource. Many entanglement generation protocols kind of proceeds like this. You have some atomic qubit that emits a photonic qubit that is entangled with the atomic qubit. So this red qubit is an optically active qubit, for example, an electron spin of a color center's qubit. And then you take these two photonic qubits, they propagate over some lossy channel, and you do a Bell state measurement using usually a beam splitter followed by photon detectors. And if this Bell measurement is successful, you have these two atomic qubits get entangled. And in the meantime, you load these qubits into longer-lived nuclear spin qubits of the silicon vacancies, and you get an entangled state with some probability across a lossy channel distance. Now, back in 2017, Stefano Pirandola and some others, they wrote a paper which was where they proved the capacity of generating entanglement in terms of qubits that you can entangle in pairs per transmitted optical mode over the channel. And this formula, negative log 1 minus square root of eta, the square root of eta is the loss of this half of this channel segment. Okay, so if you had a full channel with just a fiber connection, this will be just the transmissivity of that channel. So all of these plots that you're seeing here, they are from all these various papers on different forms of encoding of the qubit in this photonic mode. GKP, dual rail, single rail, cat state encoding, and it's the most recent paper with Liang Jiang and my former student Prajit. We came up with a scheme that you can use GKP qubits that can encode multiple qubits in a single optical mode entangled with a register of quantum memories on both sides that can get asymptotically close to this capacity in the low loss regime. But there's a whole lot of theory and experimental work in just establishing entanglement across a link. So your end product is a heralded entanglement of good enough quality. And then from there, what you do is that you take many of such entangled states over segments of lossy channels, and then you do Bell measurements or GHZ state projective measurements to connect those entangled fragments into longer distances. Now, when you take two entangled states and do a Bell state measurement in between to lengthen the reach of entanglement, you drop the fidelity of that entangled state. Okay, so you cannot just use Bell measurements to lengthen the reach of entangled states. You have to also perform a different operation called entanglement distillation. So there you take multiple copies of entangled states of a given fidelity across the same length of channel, and then you use local operations and classical communications across them to distill fewer copies of better quality entanglement. So this whole research in quantum is basically an art and science of how you combine these two types of tasks, one being distilling entanglement over a given reach of channel to improve the fidelity, but you lose the number of entangled states, versus connecting entangled states over different fragments using Bell measurements or GHZ projections to lengthen the reach of entanglement, but the fidelity drops. But the end product of most of these repeater analysis, there's lots and lots of work out there. This is just a plot from a recent paper we did on all photonic repeaters using atomic quantum memories to generate photonic cluster states. This black line is that repeater-less formula. This is the rate you will get as a function of distance if you don't use repeaters, and if you do use repeaters, you outperform them. For the rest of my talk, I'll just focus on this entanglement distillation piece and show you how to think about entanglement distillation What role does error correcting codes play there? And how do you design entanglement distillation schemes that are pursuant to the way you can do quantum logic in atomic quantum memories? Okay, so the most basic primitive of the earliest form of distillation, there's actually 2 or 3 different well-known papers, one called the DEMS protocol, one is the Deutsch protocol. They both look kind of like that. So you have 2 noisy bell states, some fidelity Fn, and then you perform a 2-qubit gate on both sides. Well, if these are, depending upon if these are bell states or a graph state, this could be a control naught or a control Z gate. And then you measure one of these qubits on each side, and based on the measurement result, you might perform a Pauli recovery channel over here. And the end result is that one of these 2 qubits on both sides survive, and its fidelity hopefully is higher than the fidelity of the original entangled state if the input fidelity, Fn, was higher than a certain threshold. Okay, this is very, very well known. Now, the way this generalizes to more complicated protocols. So first of all, this has some success probability of less than 1. There's a whole host of papers. I think Charlie Bennett's paper from '96, probably the earliest one in this regard, but there's lots and lots of very interesting work by Duran Briegel. Mark Wilde did this nice work on convolutional entanglement distillation and so forth. The idea, they're all very similar in spirit, that you now take n entangled states, so fidelity Fn, and then you perform a recovery operation that kind of looks like a decoding of a stabilizer code, where you perform local operations and classical communications on both sides, and then you distill k qubits of a better fidelity. And there's a beautiful connection between the theory of quantum forward error correction and entanglement distillation. The similarity between them is very, very similar to, in classical communications, we talk about forward error correction and distributed source compression. The connection between those 2 tasks in classical is similar to these 2 tasks in quantum communications. Now, the earliest form of code-based entanglement distillation, this is a nice PhD thesis, but there's lots of papers on it. So these are your n noisy bell states, and you perform a stabilizer measurement. And by the way, these stabilizer measurements are non-destructive measurements. So the output are still these 5 qubits I'm showing. They go through some recovery gates, and which are based on the measurement result, followed by some unitary decoding circuit, which distills out the k distilled bell states, and you discard this n minus k qubits. An improved protocol, an alternative protocol, which eliminates the stabilizer measurement step, which was in these 2 papers, they were developed. So you apply a decoder followed by hard single qubit measurements on these n minus k qubits. And then you measure these stabilizer parities, which are then fed into a recovery operation, which is a unitary, and you get these k distilled bell states. And then this paper that we wrote last year, we further improved this, which is inspired by a measurement-based model of quantum computing, where you eliminate, everything is measurement. So this is a stabilizer measurement. These are single qubit measurements, and you have a recovery gate operation, and this results in a constant depth circuit for entanglement distillation, and it's purely measurement-based model. So this particular decoder for distillation feeds into what I'm going to say next about where you even eliminate the need of a circuit. You just do everything with just cluster state and a measurement. But this paper's decoder is what is really feeds into the work that I'm going to talk about. So this is just a replica of the same figure I showed in the previous slide. Okay, so now the thing is that when I show something like a stabilizer projective measurement like this, what you really are doing experimentally is for each stabilizer measurement, you bring in an ancilla and a unitary, and then you make a hard measurement on that ancilla, so that your qubits at the end are left over. So you have to bring in these ancillas and make measurements. And each of these blue boxes is a collection of 2 qubit and single qubit gates. Now, in many qubit forms, for example, in atomic qubits, inline quantum logic, meaning doing a control NOT gate between 2 different silicon vacancy centers in diamond, is very hard. What you can do, though, is that you can generate entanglement among different qubits using photonic Bell measurement-based heralding, like I said in my previous slide when I started talking about quantum communication. But having 5 qubits and doing 2-qubit gate here, another 2-qubit gate there, another single, those are very hard. So that stabilizer projection that I've drawn, that's a hard step. So in order to mitigate that, what we did is that we started thinking about how do we construct a purely measurement-based protocol which does not rely on these inline quantum logic. So here's the way we thought about the protocol without going into the mathematical details. How much time do I have left? Okay, sounds good. Thank you. So these red circles are qubits that are remote qubits that are in noisy entangled states. I'm showing you these are your noisy entangled states over the channel. Imagine you have ideal Bell states. These blue and green circles are ideal Bell states. And you do a Bell basis measurement on the blue and the red qubits. Now, if these are ideal Bell measurements, then what will happen is that your entangled state that was originally on the red qubits will be transferred over onto the green qubits. It's kind of silly. Like why I'm doing this will be clear in the next step. But here I'm just showing you that if I bring in Bell states, ideal Bell states, I can always transfer over the entanglement that the channel gave me onto the green qubits. Now, these local noiseless Bell states will carry over the entanglement. Now then what we could do is that once you have transferred over the entanglement from the red qubits to the green qubits, by the way, you may need some local poly corrections based on these measurements. The Bell state measurements measure 1 of 4 Bell states, so you may have to apply some correction to these green qubits to get the same Bell state on these green qubits. And then from these entangled states, we distill the n-entangled states formed by the green qubits onto k output states in the standard Bell states. So you can distill entanglement into k good quality Bell states using stabilizer measurements on these green qubits, like I said in the previous slide. This is how originally the measurement-based, the entanglement distillation, code-based distillation was developed. But now the idea is that, well, instead of what you would do is that to distill entanglement, you perform a measurement on these n qubits preceded by a unitary to get these k distilled physical qubits. But then instead of doing that, why not prepare an entangled state among the blue and the green qubits together, this n plus k qubit entangled state, and think of this as a resource state such that this measurement directly transfers over. So does 2 things. It does this measurement, it transfers the entanglement that was on your noisy entangled states onto the green qubits, but also does the decoding steps so that now you go from these n entangled states to k better quality entangled states directly over the channel. So this is an example. So you have 4 entangled states across the channel that was delivered, and you have this 6 qubit local graph state, which is generated from this 422 code. And then you do these Bell state measurements on these 4 qubits, and the result is that you get 2 entangled states that are of higher fidelity. And the nice thing is that these 4 measurements that you are doing, these 4 measurements are the same exact Bell state measurement, where these red qubits, for example, could be the optically active electron spin of a silicon vacancy center. And these blue qubits could be the nuclear spins of that same silicon vacancy center into which you can do 2-qubit gates very reliably. So you're never actually doing a 2-qubit gate between 2 distinct color centers, but you're just doing a single shot 2-qubit measurement, a Bell basis measurement on all of the qubits in the array. And all these red and blue qubits are gone, and you're left with these green qubits, which are in a pure and better quality entangled state. So the problem basically boils down to taking an error correcting code and translating that into this graph state, and then preparing that local graph state, and you just measure off these qubits and you have distillation. So I don't think I'm going to go through the details of this, the math of this distillation because of the time, but very, very quickly, the stabilizer generators of this n plus k qubit state involves the stabilizer generators of the original code. These GIs are the code stabilizers, so there are n minus k of them, and they're k plus k, so they're n minus k plus k plus k, so they're n plus k stabilizer generators of this whole n plus k qubit state, where these x bar and the z bar are the poly operators of the logical qubit, the jth logical qubit, and these xn plus j and zn plus j are the poly operators of the n plus jth physical qubit. So you can think of the blue and the green state as a logical physical Bell state. So these bars are the logical qubits and these kets are the physical qubits. So you're, by these Bell measurements on these qubits, you're basically doing a swap and a cleanup together in one step. And the way this thing works, that you're making these Bell state measurements can be thought of as the XX and ZZ stabilizer projectors. This is the parity check matrix of the code. Alice sends her 2n bits over to Bob. This SI and TI are her parity measurements from these two projectors. Bob computes the overall parities by adding his and her Alice's parity measurements, calculates syndrome, bit and phase flips, and makes the correction operators on these green qubits, and you get the entangled states, just exactly how you would have gotten in the circuit model, but using the measurement-based model of quantum computing. There's an alternative you can do that. Bob just verifies the syndrome to be 0, and then if it determines to whether installation succeeds or fails, which actually succeeds with a higher probability, but it can only tolerate more errors, like the D-1 errors, but it's probabilistic. So it requires two-way classical communication, whereas the previous protocol that I just described is a deterministic protocol. Okay, so now how do you take this step of distillation and turn that into a quantum repeater? So now there is another realization that comes in, is that now let's say that what I was talking about is just a step. Imagine these blue qubits here. This column is basically this column, or a single link. Now, at a repeater node, you have a right part of this portion, and maybe a left portion over here, which is sitting at one repeater node. What we realize is that why do we need these these green qubits? You can just consume, you can get rid of this and directly prepare an encoded k logical qubit, n physical qubit, so 2n physical qubits resource state that every repeater generates. And you can fault tolerantly, you can teleport your entangled state across the whole chain. So now this resource state is a logical k qubit Bell state involving n qubits on each side. So now each node transmits its computed bit all the way to the end, and you calculate an overall phase flip and a bit flip error. And given that the neighboring nodes share noisy Bell states with some fidelity, say infidelity P, but for the physical qubit error, the quantum error correction reduces this to some logical error, which is dependent on P and the error correction code. And if PL is small enough, the logical error, then if you over n hops, the overall error goes roughly as 1 minus n times PL for small l. Okay, so then the next question is that how do you do the error analysis of this protocol? So there are multiple places that error can happen, which you can all subsume into the errors into the channel distributed noisy Bell state. So you don't have to worry about error in the resource state preparation. So for example, the resource state, you can model, let's say, a stabilizer states with each qubit subject to a depolarizing channel with some error probability PR. And the input Bell states, the channel distributed entangled states have some error probability on each qubit, which we model as a depolarizing error, as PB. And the Bell measurements has some error probability. The recovery polygates are assumed to be error-free. All of these errors can be consumed and subsumed into a combined error onto that remote Bell state, so that you can forget about that and assume that your resource state is perfectly error-free. And this effective error PT is basically the effective error per repeater segment, to which the code reduces to some logical error. And after n hops, your fidelity of the final distributed Bell state can be approximated as this 1 minus n times PL. As I said before, this term just accounts for the uncoded output qubits at those green qubits at the two n nodes. Now, let me just click through this part because I don't have as much time to go through it. But for hypergraph product codes, which have these are constant rate codes whose minimum distance scales as roughly the square root of the code length, very simple sort of arguments, you can prove that you can achieve any end-to-end target fidelity by increasing the code size n only polylogarithmically with the overall distance while maintaining constant encoding rate. And these are just some simulation results of the hypergraph product code. For this particular code family, as long as the overall error is below this 4.65%, you can do fault-tolerant quantum communication. Given that I don't have any time left, let me skip this portion of preparing the resource state, which is the interesting problem here. I'll just tell that in words is when I give you that graph state that comes from an error correction code, there's a very interesting open problem on how do you prepare that. Like, I told you how you can prepare an edge of a graph by having 2 qubits emit photonic qubits and do a Bell measurement between, and then take those 2 qubits from the electron spins of the color centers and move them over to nuclear spins, which are long-lived quantum memories. That frees up the electron spins after you have moved them over to nuclear spins, which can emit photons again and entangle themselves with the other qubits. And then you can do 2 qubit gates between electron and nuclear spin qubits to create a 3 qubit, a 2-edge entangled state. And you can parallelize this, you can stitch this together. So there's a very interesting open question of how you, in the most resource sufficient way, map a graph state into instructions on photonic heralded edge preparation and 2 qubit measurements and 2 qubit gates at each of those color center atomic sites. And this maps to a very interesting graph theory problem that is known as maximum independent sets, where you can parallelize the generation of these entangled states, which we are looking into. But with that, let me switch to my last slide, and I'll conclude, and happy to discuss the part that I skipped over in coffee breaks. Quantum repeater design, there's one interesting thing that comes up often is the need for quantum logic on your qubits and scalability in terms of the number of qubits you have and their photon interfaces. So it turns out that based on the quantum memory platforms we have today, like color centers, they're very scalable, very efficient photon interfaces, but not very good quality quantum logic. You can't do 2 qubit inline gates, like I said. Trapped ions, for example, they have very good quantum gates available, but not as scalable and not as high efficiency photon interfaces. So it turns out you can put together hybrid repeater protocols that have color center nodes, a few hops, and then you go over to a trapped ion node that takes the heavy duty of error correction, and you pass over the baton to another color center node. So there's a very interesting work by Stav Haldar with myself and Don Towsley and Philip Prospedek. Rate threshold adaptive coding. This is going to come out in IEEE Quantum soon. Extensions to multipartite entanglement distributions in a network. And then finally, I would point out this very recent paper, actually it appeared in Optica Quantum, on capacity achieving entanglement distribution across a bank of quantum memories over a single channel that asymptotically achieves this PLOB bound, this negative log 1 minus eta qubits per mode, when eta is very close to 1, which is a regime which is very interesting for generating entanglement locally across qubits, for example, within a quantum computer. And none of the known formats of encoding qubit in a photon, including dual rail, single rail, CAT state, they don't achieve that this high capacity portion of this negative log 1 minus eta curve because they cannot encode more than 1 qubit in a single photonic mode. So this GKP QDIT scheme that we published, that solves that problem. All right, with that, I'm going to stop, and if there is any time, happy to take questions.
Many thanks for a very nice lecture. So maybe we have only 1 minute for one question. So in the current optical channels, is it single measurement things that we are implementing today, or is there any joint measurements that we do to extract information, going away from entanglement, just from optical channels? I mean,
so
you're the expert
yeah, this paper here on the bottom, the 2025 paper, this Nature Communications paper over here. Here we demonstrated a joint detection measurement that achieved for the first time a tiny bit higher capacity than the best capacity you could achieve with BPSK modulation with only single symbol receivers. So this was the first demonstration of super additivity, but proof of concept experiment. I wouldn't say this is ready to be deployed or anything. This is a bulky experiment. There is a very interesting new design of a fully programmable time mode unitary that can take a whole long sequence of optical pulses and do arbitrary linear operations among them, which my colleague Chauhan Sui, he's right now building in an on-chip platform. But in order for you to get all the way to the Holevo capacity, the best possible performance you can get, just linear processing of optical modes doesn't suffice. You have to bring in squeezing. But if you allow for squeezing and linear optics and photon detection, there's a beautiful theorem from Seth Lloyd and then who else was the co-author on that? Brownstein, that showed universality. Like if I give you all Gaussian operations and one non-Gaussian measurement or one non-Gaussian state, you can do everything you want. But that doesn't readily translate to a prescription where I give you this measurement and that translates into something that you can realize in the lab. So there's lots of very interesting open questions here, theory questions.
See, but when you say super additivity, right? The super additivity in information theory is slightly different from what you're saying.
This is a different super additivity. There's two notions of super additivity. One where it says using entanglement at the channel input gives you a higher capacity. That is sometimes what people will call super additivity. And Matt Hastings showed in 2008 that there are channels that are super additive, meaning entanglement at the input can help you higher capacity. Optical channels, lossy, noisy optical channels are not super additive at the input, okay? But there is still super additivity in the output on the receiver side, meaning if your receiver acts on one symbol at a time, there's a certain maximum capacity you can get.
That is product measurement.
Product measurement, correct.
See, even non-product measurements, you can go beyond what is the regularization. That is what is referred to as super additivity, right? So yes, that is slightly different from yours, because here you're just looking at non-product measurements of length 8. But then I can build a code on top of that.
No, of course, yeah. So this is, I'm just showing an example of an 8, but this is just to give you an example. But if you wanted to get to Holevo capacity, your measurement has to act on a growing long block of code word.
No, but even the Holevo capacity is not optimal, because you can take the n-letter version of the Holevo capacity, which is, that is super additive.
No, not for optical communications. In 2004, we proved that the single letter Holevo information even for the lossy, noisy optical channel is optimum. You cannot go beyond that.
In general?
I'm not talking about general. Okay. Optical communications, it doesn't help you to use any entangled state of the transmitter. It doesn't help you to use non-coherent states of the transmitter. It does help to use joint measurements on the receiver side, but the single letter Holevo capacity is optimum. You cannot improve that by regularization.
Okay, thanks the speaker again.
Thank you.